Yeah, they had them out yesterday.
So stoked all day for this. I woke up, it's time for fishy. I'm like, what? I gotta get it.
It will be weird because they're like, they look like they're freeze dried.
Yeah, they're all weird and stuff.
No, they're not freeze dried.
They're dehydrated, looks like they were sitting under the sun for a minute.
Well,
I'm used to cutting up like freshly murdered fish.
well,
That's
But we need to actually look at the insides because normally you just cut them and you scrape their guts out, throw it back in the river.
yeah.
right.
Well, it's good for the river to throw that stuff back in there. Feeds the
Oh.
Yeah.
ecosystem. Oh yeah.
We're probably, I wonder if she's skipping 9 or if we're going to.
We're going to 9 on Tuesday.
Chapter 9?
Or I'm
No,
sorry.
for lecture here
Yeah,
we're
I'm sorry.
doing.
I just realized it was.
We just finished 8, but she wanted to be on 10 today, so I don't know what we're
We're probably gonna do 9 and 10.
probably gonna skim through 9 real fast
Yeah.
and then try and get to 10 today. Is her plan.
She's got chapter 10 up on here.
Yeah.
God, I hate the summer term so much because of that.
So we're probably just skipping
Just
9.
burning through it.
Until maybe next week.
We're probably just skipping 9. So we're gonna have to read 9 on our own. That's what I think I'm gathering. She has 10 up though, Kai. I'm
Yeah.
pulling out my book.
Says chapter 10 on.
So much easier to follow her on the book than it is to follow her like in the slides. Is Charlene not even coming to lecture today?
Probably not. I don't know. I'm thinking, sorry, I was thinking that.
Oh, naturally, she won't be here for lab, that's for sure.
She might be, I'm not sure. I like answered too fast without like thinking, oh, wow, no. I don't think she would.
I wonder if she knew it wasn't gonna be like super bloody.
Yeah, I know, there's like
Because
gonna
that's,
be no
that's
blood.
usually like what people hesitate about,
Yeah, that
cutting
or
an
just
animal up is because of all the blood and stuff.
I wouldn't wish that.
I didn't, so somebody cut one up behind us, like last week,
These have
and
been
it didn't
embalmed.
smell bad.
These have been embalmed.
Yeah, they're like dry and
They're
they're like
weird looking.
beef jerky.
Yeah, they
Or
don't
like,
look
or they look more like a raisin. They all shrunk, like, they've been sitting in water, but.
Looks like they were dehydrated in a dehydrator for a while.
Yeah. So I doubt they're gonna smell, because the school would hate that. It's,
They're gonna have the whatever chemical they use to preserve it smell is what it's gonna be. Mhm. Woo! Yeah, that's what I think. Oops. All right. Are we doing chapter 9 or chapter 10 today?
Hopefully. All right, we'll save this
I was
for
like, I
later.
don't know where to start.
So yeah, sorry, I'm showing chapter 10 right now.
Are you gonna post your notes soon?
Yes, I will hopefully post them in class. I've just been having computer issues.
Yeah, computer issues so much fun.
Yeah, well, the only reason I have issues with this computer is because they don't allow us to do anything. So I can't install any programs, I can't update it, like,
You have to call the people that.
yeah,
So stupid. Hey, come fix what I can do myself.
exactly. Anyways, yeah, I will post notes in class today, hopefully of 9 and 10. So let's go through chapter 9. And so like we said, just a quick reminder, exam is coming up on Thursday. But again, try not to stress, I'll keep it easy level. And don't forget, right, I have office hours after every class, basically, so stick around. Or any other time, I'm free to meet. And so tides are just defined as the rhythmic rise and fall of the sea level. And I'm sure we've seen this before, right? We go out to the ocean. That's why we're planning our coastal trip at a certain time. Because of the tides, we have to go during the low tide so we can actually see things. And so we'll talk about why tides exist. So they're caused at least, well, in part by the gravitational attraction of the sun, moon, and earth, but then also, right, the balance of centripetal force, which we will talk about in more detail. And of course, you know, the earth is not perfect, it's on an axis, and then even, right, our orbit around the sun is not perfect. And so all these different attractive forces is what create our different tidal patterns, and then obviously we also have continents in the middle of these great sloshing tides, so that also gets in the way.
Does the Coriolis effect affect tides?
Yeah, so that's, yeah, so another complications that, right, in addition to sloshing around our continents, then yeah, the Coriolis effect is still going to have some effect as well. And so again, tides just defined as a periodic raising and lowering of the ocean sea level. They occur daily. And so our gravitational laws and our centripetal force explain this relationship. And so Newton started at least understanding kind of the gravitational potential forces. And of course, you know, early sailors recognized tides. All right, so your book, in my opinion, explains things kind of strangely. So let's start off, I'll point out where I think the book is deviant. All right, so first let's define this barycenter. So this is, we're just thinking about, right? So we have our Earth and our Moon. So they're rotating, right, around the sun. But really, what's rotating around the sun? Well, mathematically, right, that's going to be this point, your barycenter, aka your balance point. And so what do you kind of notice about that barycenter? Yeah, so it's off-center and it's located in the Earth too. So that's already kind of an issue, right? Or why we have a little bit of an imbalance. But all we're saying is, again, when we calculate our forces, essentially this is our our mass and center, so our distance. Oh, that was terrible. So, right, our distance. And I'm probably going to get too excited because there's physics and math, which just gets me going too much, but I'm trying to keep it simple. All right, so we have, right, our balance point of our mass. So that's all that's stating here with our barycenter. And again, that's just the average of our masses of the Earth and the Moon, and obviously, like we mentioned, it's centered on the Earth, since the Earth is much larger than the Moon.
So would that be like our strip of paper in our last lab? Would that be the barycenter?
Yeah, so like that distance, or at least like, yeah, with the sun though.
Yeah.
So that, yeah,
Okay.
hopefully that made sense. So that's just our balance point. And so now a little bit of math here. So I would give you the formula and write some questions on an exam would be, right, relating distance. So what do we notice about the distance here? So it's radius. So it's squared, exactly. So that's basically, right, the distance between your objects. So as that goes out, it's squared. So that's going to end up being, you know, an exponential factor. And so as our distance increases, obviously that force decreases. So that's, we're not going to go through the math. That would be too exciting for me. But that's why, right, the moon plays a big part in these gravitational forces, right? Because we have the huge sun also playing a portion, and of course, right, Earth, tiny moon. And even though, right, moon is tiny, so, right, mass, so whatever forces you're calculating, so you have to calculate between each force. And again, I'm going to get too excited. So calculating your gravitational potential energy. So that's just your force of gravity, right? So what's keeping you on the Earth? So this is keeping us right on our path. So connected, oops, sorry, wrong way. Connected to the sun on our elliptical orbit, right? But again, the moon matters because even though mass is much, much smaller than the sun, it's also, right, r squared, much, much closer. So we still have to take into account all these forces. Is everyone still following?
You lost me at squared.
Squared, really?
No.
Okay. I can't be sure. So yeah, distance, so as our R increases, again, force decreases. And so kind of showing astronaut in space floating away as he gets away from the Earth. So now not tied down. And so this is fine. This picture is fine. I'm going to insert another picture. All right, so, right, our gravitational force. So this is fine, this word center seeking. And so now, this is, don't give scientists too many toys time. So, right, we're circulating the sun with our Berry center. So our gravitational pull is what's keeping us going around. Just the same for the moon, right? So think about that. So it's your gravitational force. And we'll talk about what's keeping it in motion, because the next question is, well, why don't we just, crash into the sun? But we'll get there. And this, of course, tethers the Earth and the moon together. So at some point, at least so the theory goes, right, didn't the moon crash into the Earth partly or something, and then it got trapped in its trajectory. So that's how things get trapped. So, right, they'll be traveling along happily or flying through space, and then if it gets caught in a large enough object, like the moon got caught, right, so then it starts going out. So that's, oops, those are your two forces. And we'll go through that again and probably smack myself a few more times. And so now we're looking, and so our strongest points where it's going to feel this, and that's where you made your little elongated blobs of your little diagram, is it's feeling it right around the moon, so that's where you get the little bulges. And so this is where I start having some issues with your textbook. So it says that the centripetal force is pointing inward, but that doesn't make sense, right?
Oh, because the force is, all the weight from the object is forcing its weight and its momentum outwards, right?
Yeah. So exactly.
Because
And
you're not spinning, the ball's spinning.
yeah, so it's spinning, right, and what's keeping it tethered, because it says string supplies centripetal force. That's not true, right? It's just literally, there's a physical string that's applying force. And what's keeping it, though, what's keeping it outward, really?
Itself.
The object.
Yeah, the centripetal force, though. So that's why I think your book's completely backwards, right? So centripetal force, if we were to snip this while in motion, right, it would fly out at one of y'all. And so that's from centripetal force. And so again, that's how it got caught. So moving along, gets caught tangentially in the gravitational, and then whoop, now it's circulating. So yeah, this is where I take issue with your book. I don't know what it was trying to say, or maybe it was trying to, I don't know. I really don't know what was going on.
Well, maybe it's saying the string is pulling it back.
Yeah, but that's, yeah,
It
but
wouldn't be pulling
centripetal,
if it didn't have anything pulling against it.
right, so it's pulling, the string is pulling against the centripetal force. That's what,
That's what I think.
yeah, so it should be string supplies force against, right? To keep in, because that's the balance, is your string's holding it versus the centripetal force where it's trying to get away from you, but that motion keeps it going and the string keeps it tethered. So yeah, your book looks wrong, so,
So the string kind of represents the gravity.
right, so string, so let's write that very clearly. So the string is gravity. So, right, our FG calculation. And obviously, this gets a little tricky with our, our sun, our moon, our earth, and all that. But that's the main thing, is we could balance those forces. We could see, right, our total force of gravity of everything, and then our centripetal force. And so this is another graph that I take issue with, but I'm going to slap a better one on right now. So I have no idea what they were trying to say. I was trying to give your book the benefit of the doubt, and like maybe I just wasn't understanding.
I Googled it if that helps, and centripetal force is the opposite of centrifugal force. It's the force acting on an object in a curvilinear motion, so it's making it a circle.
Yes, but then it'd be going outward. So was that centrifugal though?
Yeah.
So that'd be a little different. So that's like when you spin stuff, and then the difference in like gravity and the density separates it. But yeah, but yeah, that's why I say your book. So when you read this, like your book, I don't know what happened. Again, maybe I just misread it and it's just worded poorly, but I think it says the complete opposite. And so let's kind of ignore this. Let's paste in this graph. So this is a much simpler and also makes sense representation. So let's ignore this, because like I said, I don't know what they were trying to say. And so again, we have our centrifugal force around, oh, that's funny, due to, now they use those terms interchangeably. So due to Earth's revolution, so right, just our force moving around. Then we have gravitational force due to the moon. And then your tide is resulting from basically inequalities of these forces, right? So overall, if we were just calculating the forces for the barometric center, right, that would be equal. Those forces would be equal at the center, but we just said, well, our center isn't actually center of the Earth. So now this gives us all these unequal forces.
That center that you showed us, is that for the moon or for the sun?
That's the average of the moon and the Earth rotating around the sun. Yeah, so that's their like main center as they're rotating, but then, right, the moon also rotates around the Earth, so everything's a little off.
Because of the tilt?
That's also a part of it. So it's also the center, so it's also the center of their rotation is off, of the moon and the Earth, right? So everything is off. So both, yeah, it's both the center as it goes around the sun, so that's a little wobbly. Then it's the center as the moon rotates as well, so that's a little wobbly. And it's at an axis, so it's also a little wobbly. Yeah. And so even this, so you've caught on, even this is an over-idealized picture, right? Because we're not taking into account that rotation at all. We're just pretending we're an up-down Earth, and that would mean the side facing the moon, right, would experience the greatest gravitational pull towards the moon, so that's just the force of it being pulled towards. Then here's our centripetal force, so going outward, and then our resultant force, so this is our tide, would be a little bit pointing towards the moon here. And so it tells us as well, So at this point, since we have a greater, and this is just slightly, because again, we're uneven, so this side of the Earth is pointing towards the moon, and so now it's going to be bulging outward. So our gravity force, right, is greater than our centripetal force. And so that means that, again, our overall is great here at our A. And so if we look at B, so B has about the same force as A. It's just going in the opposite direction. And except here, so we have less gravitational force because we're a little bit further away. But now our centripetal force is going to dominate, so it's trying to go outward. So once again, we get an outward bulge though, but now facing away from the moon, right? Because you have your two extremes, either near the moon, closest to the moon, and then those unequal forces gives us those bulges, just like you drew on your little diagram.
I'm not sure I understand. I understand why it would bulge towards the moon, I think.
So here, so now it's unequal again. So again, it's also, right, our center is unequal. And so over here, and it's just distance. So now it's almost, just look at the radius issue. So this would be, let's just call it R1 versus, if we were doing the math, right, you could literally calculate it for every point. Because again, the math is for the center, like the true theoretical math. But then if we're calculating the math at every point on the Earth, it's slightly different, right? So then we take whatever this difference is, we could compare the factor of the difference in radius, and that would tell us, right, that now at this point the gravitational force is less. So our centripetal force doesn't really change, right? Yeah, but it's just, yeah, at this point, so over here, right, gravitational is going this way, centripetal is going that way, but gravitational is more, so it still bulges. But then on the far side, we have more centripetal force, less gravitational, but this dominates, so it bulges. Yeah. No, it's difficult because there's a lot of forces and we're spinning around, right? There's like two spinning systems to consider in this, so. And again, the moon dominates because of how much closer. So hence we're just looking at the moon here. And so approximately in the center here in C, wherever the center of the Earth, then that's where we expect it to almost be no force. And so that would be right all along, again, in our theoretical Earth that doesn't have a tilt, it would go up and down. So all along this line, right, the forces, there'd be no force. Idealized. So idealized, no tides, since F gravity equals F centripetal. Also, if anyone's in the chat, say hi. Expecting some people online. All right, so we're okay so far. So I apologize that your book has an error. I would have warned y'all if I had taught this class before. All right, so this graph is fine from your book. So here it's showing, right, the center here, where we would, again, have less tides and then are bulging out. So that's what it's trying to demonstrate there. In our moon, or away from the moon. And so we mentioned those were our lunar bulges. So this graph, right, is fine. So again, we're seeing the bulging because of the inequality in forces. And so then we have our tidal period. So this is just defined as time between high tides. And so what's kind of the interesting thing about the lunar day and the solar day? Sorry, what'd you say?
One's 50 minutes longer.
Yeah, so one's 50 minutes longer. And so because of that, we even saw, so remember from the lab, we're trying to compare the title of data. I think, what was the Excel file, like 2021 data, 2022 data, but then trying to overlay it with 2023, we could already see how the time has shifted. And so all of that just starts with that 50 minutes. So every day, right, the tide will be 50 minutes later, 50 minutes later. And hence why we use the nice coastal chart website at U.S. Harbors, so we know when to go to the coast and why that time's always changing.
That's also why we get full moons and such, right? Because it's longer.
Well, that's probably why the cycle, because of, yeah, why the length of the moon cycle is funny, but yeah. But that's also from just rotating around and then with the sun, which we'll get at. So then that means our high tides are 12 hours and 25 minutes apart, so obviously that doesn't match up with our nice 12-hour days. And so the sun can have a small effect as well. And so those are called solar bulges, so that would be similar to lunar bulges, but less than half the size. And so like we were kind of talking about earlier, that the moon is a lot closer, so it exerts a greater gravitational force, at least in terms of the tides. And so a flood tide is just when water moves away from the shore. And right, we can see that the water receding away, or sorry, it moves towards the shore. I read that wrong. So it moves towards the shore, so flooding in, and then ebb is moving away. And so of course our tidal bulges are relative to the sun's and moon's position. And of course Earth's rotation, right, will keep moving different locations onto the bulge. And so we could look up, right, tidal ranges for different areas. I'm trying to remember, or some of the extreme examples given in the book. No, I can't. But obviously, right, different places can experience different highs and lows. I think the book mentioned like some extremes of 17 feet in difference, and other places much smaller, maybe like 10 centimeters. And then we have this special term, if I can present.
I just wrote it down. How do you say that?
Syzygy? I should. Syzygy? But that's when our moon, sun, and earth are all aligned. And so that gives us, right, our greatest difference, or our greatest high tides and low tides. And so then, so let's look at the picture better. So right in alignment, so we get the greatest bulges. And then so moon continues rotating, and so known as the first quarter moon or the third quarter moon. So either one of those conditions, then we get these different bulges. So now the bulges are kind of going in opposing effects, and so that gives you what are called the neap tides, so those smaller tides, versus the spring tides. And so spring tides, remember, they're not just for spring, but it's supposed to be, right, water springing. And so again, those happen with either your new moons or your full moons. So when, right, you have the dark moon when it's blocked off and you can't see it, right, it's all black, then versus a full moon where it does get sun so you can see it. And so again, that's where you have your greatest tidal ranges. So it probably, these would be important terms, to know. So you want to know spring tides are your greatest ones with the new or the full moons, and your neap tides are with your quarters and the least tidal range. So that's fairly basic. And again, a new moon. So I probably won't get too detailed on like the new moon versus full moon. That's still at least good to know, right? So the moon is between the earth and the sun. So again, it's getting the light blocked, so it looks black. And so again, I'm not going to test you on probably all these, the waxing crescent, waxing gibbous, waning. But that's just nice to appreciate. So of course, right, the moon, not to further complicate things, has all these different positions in between. So that's going to affect the tide. Keep moving on. And so yes, complicating factors, which you all pointed out, is we're at an angle. And so the sun to earth distance tends to be about 23.5 degrees north or south of the equator. So we looked at, right, depending on whether it's summer or winter, that changes. So your bulges tend to be around there. And so moon to earth is about 28. And so there, again, your tidal bulge should be somewhere around this 28.5 degrees, at least, right, the greatest. So now, not at the equator from our idealized model, moved up, again, just from our tilt of the earth. And I could get the globe if we need it. And so again, that gives us more unequal tides, right, more fun. So again, difficult to just make it idealized. And so the sun does, again, have a little effect. And so as it rotates around the sun, it is closest to the sun, or has the greatest range in January, when it's just physically closer, and then the least range in July. So that's from the sun. It's just the greatest, what it's called, the perihelion, when it's rotating around and referring to those forces.
In the book it says peri is near and helios is sun.
Yeah, and so you could say, right, aphelion would be away from the sun. Is that Latin?
Probably.
And so these were the terms, so right, the helion referring to the sun, and then moon around the earth. So tidal range greatest at the perigee, so moon closest to the earth, and so we have those terms peri again, so giving us some clues. And so it would be least at the apogee. And so this cycle is 27.5 days, almost a month. And so now we can imagine if these phenomenon line up, right? So we have our spring tide from our moon, and then it's not only our spring tide, so new moon or full moon, it's also closest. So now we're really feeling the effects, right? So we might get an exceptionally high tidal range, and that apparently happens every 1.5 years or so. I like that exaggeration. And so we can also see this, so I'm sure y'all have heard of the term supermoon, right? And so that happens during the perigee, so the moon looks about, they say 14% larger.
We had one just like last week, didn't we?
Oh, I totally missed that one.
Yeah, I went outside.
It was really bright.
There's pictures of it.
Nice. And so during the apogee, the moon appears smaller, so I'm sure, no, today's cell phones get like crazy pictures of the moon.
Yeah, you can see like all the craters on it and stuff.
So this is again our idealized tides. So we would expect 2 high tides and 2 low tides per lunar day. And so again, we can see these bulges. So again, the issue is we're at a tilt. So this is, again, where our bulges are. And so now we can see the delay and our difference in north and southern hemispheres. And so again, from our bulges, our 28 degrees north latitude observer would be experiencing our high tide, so just starting at time 0. And then comparatively, on the south, right, they would get that same high tide, but now it's just delayed by 12 hours. Of course, right, rotating, and then it gets closer to the moon. It's now rotating. Again, we can just see our cycle, high tide, low tide. And obviously this is complicated by the continents, friction, right, seafloor features, all of that can of course modify our tidal bulges. And so tides are just shallow water waves with speed determined by depth of water. So right, just recall our formula from last chapter. Right, the 1/20 of L, and then you can invoke speed. And again, how it might come up on exam would probably be some word problem of like, a wave is coming in with a wavelength of blah. What conditions would it be? And I'll give you formulas for like shallow and the transitional, etc. So you'll have all the formulas. It's just like plugging it in, applying it, reading, that sort of thing. All right. And of course, right, with all of this, our idealized tidal bulges cannot form. And of course, we also have Earth's rotation. And so now we have what are defined as this amphidromic points. And so essentially, this is no tidal range. And where is, I thought there was a picture that showed where there was no tidal range. Sorry. Let's ask Google, because there should have been, maybe actually I can't find it in your book. Let's look this up, because there is a mapping of this. There we go. So Wikipedia is great for science, just don't look up history or current events with it. Let's see. All right, so this is what I was talking about. So this is just a tidal map. So it's just telling you your difference in tides. And so our, again, amphidromic point is going to be these blue areas where there just happen to be kind of no tides. And, again, you kind of have to think about the continents and the forces back and forth. And so this is how it kind of maps out. And it makes sense. So we see a lot right in the South Poles And so they're kind of in the middle anyways, so those centripetal and gravitational forces are already fairly centered around there. And then they can already, right, the water can at least flow around. There is Antarctica there in the way, but, you know, that's where you don't have too many currents. And then look around. Let me get a better picture. Oops. So looking around here, right, that's at least pretty significant tidal differences, especially, you know, I'm just looking everywhere, so where we have most extremes. And again, our points kind of in the middle between continents, so you can kind of imagine, right, a huge tub, and maybe it gets a little point in the middle where all the tides and all the forces kind of balance out, so there's no really net tide movement in these areas. Again, lots in the poles, kind of gets stuck in here, looks like, right? Not a lot of tide movement in the Gulf.
So the blue is like less movement.
Yeah. So yeah, blue's the least movement. And so obviously it doesn't follow the kind of the idealized Earth. Again, all the continents, all the sea form features, everything influences this. So this is, again, why this mapping's nice. Let's insert that into the lecture notes. I don't know why your book didn't put it in. There we go. And so now this one is just kind of showing how the Earth's rotation and everything plays into a part of this delay of the lunar high tide. And you can kind of see, right, they follow these lines too. Obviously the Coriolis effect also plays a small factor, so everything's playing a little factor in here. And so this came up in your lab. So you did have to look in the book. And so there's three main tidal patterns. And so there's diurnal, so one high tide and one low tide per day. And the best thing to do is look at this graph so we can kind of see where that happens. So diurnal, so just kind of looking. So notice the Gulf again has just a diurnal pattern kind of down there.
This is for each lunar day, right?
That's what, sorry?
For each lunar day?
Yes. And then semi-diurnal is 2 high tides and 2 low tides per day. So again, you could look at the map. And again, appreciate, so the red is where it experiences that pattern. And so again, right, our Earth and continents and everything is not perfect and everything is a little off. And so there's a lot of areas with mixed tides, with a mix of either 2 high tides or 2 low tides, or they changes patterns, so changing from diurnal to semi-diurnal. And so we see that right in a lot of these blue regions. And so these are just idealized tidal patterns. So this would be our diurnal. So again, looking at our lunar hours, so 1 up, 1 down per day, so 24. There's our day versus semi-diurnal. So where's our day? Up. Our day.
So on the mixed, at different seasons or different points of time, it changes from diurnal to semi-diurnal?
Yeah, so we'd have mixed patterns like that. And so here's kind of a mixed example, and maybe even, so let's see, so this is 24 hours. So we have like all these mix of, so notice it's also not even, right? So these are pretty even, where the mix is all over the place. yeah, it still has, right, 2 high tides, 2 low tides in this case, but they're just also uneven. But yeah, the pattern could also shift to 1, and so yeah, all over the place. And so this is some more example of the data that you might see then. And so y'all got to look at some data. And so this is semi-diurnal, and so it seems pretty regular, just comparing to Boston. And then San Francisco, so this is mixed. And so you can kind of tell, right, it at least looks very uneven compared to the very regular pattern of our Boston. Bless you. And then Galveston, they have classified as both mixed and diurnal. And so you can kind of see has mainly a regular pattern, but also some irregularities. And here is a better pure diurnal picture. So again, you can see how it follows pretty regular variations. And so other factors to consider are what's called standing waves. So if you have, right, a tidal wave, well, just like we made in our water bath. So if it's reflected right by the coast, so your wave comes and it hits it, it can kind of create this standing wave, which would then kind of amplify that tidal range. So also kind of thinking about forces, so constructive interference. Uh-oh, my computer isn't charging. Come on, there we go. So here's where your book had those kind of fun facts. The Bay of Fundy in Nova Scotia is apparently the world's largest tidal range.
Does that mean it experiences all those different types of tides that we just discussed, like the different tide patterns?
No, it means that it has the greatest difference in the high tides and the low tides. So let's see. Yeah, we'd have to reference, so all this is just like extreme and tides. And just trying to overlay it with our other map. So it looks like it's in the red region, so the semi-diurnal pattern. So we could refer to another map for that. But that doesn't dictate the extremes, so it's kind of interesting. Not entirely sure why, right? It's a little above that 28 degrees that we were saying would be close to the moon. But maybe there's something weird with like the bay and other factors and how the water can flow that gives it that range. So again, right, all the features are going to influence how water flows. And so again, you can just appreciate the boats and the difference there. And so we can also have tidal bores, so that's a tide-generated wall of water. It can go up certain rivers. And so this is when you have a large spring tidal range, and so an abrupt flow tide and ebb and short ebb tide phases. So just a lot of water rising. And if you have a low-lying river with a seaward current, that can, of course, influence that as well. And so we have different currents. So we have a rotary current, and that's just defined as a counterclockwise current. So this is a current that accompanies slowly turning tide crests in a northern hemisphere basin. And a reversing current would be the other way, so again, moving in and out of narrow passages. And all of that, right, can give us whirlpool conditions. So the spinning water, so it's spinning, right, in different directions, in and out. And so sometimes, right, if you have an area of kind of trapped water, that's where you get those whirlpool conditions if it rises in with the high tide. So you can't get stuck in there. So again, flood current, just when water comes up, and ebb when water drains. And then high slack water is defined as when you have the peak of your high tide, then with no current motion, right? So it's not flooding in, it's not coming out, it's just kind of the highest point, the maximum, right, of your kind of sine curve, I guess. So thinking about it as just an oversimplified sine curve, so now, right, we're here at our high tide, so that's just defined as our peak, and then of course we go back down, ebbing, then we have our low slack phase. Oh, and they have the same thing drawn here, so right, ebbing, flowing, high stationary, high slack water, low slack water. So we mentioned whirlpools. So yes, you can get caught in them. And so what was the significance of the little fish? The grunion fish. What do you remember about the little fish?
Well, they can adapt to different, like, rapid changes, right? Isn't that kind of what they're known for, is like being able to do shallow and deeper water, or?
But they come completely out of water in summer.
Yeah, so there's, well then what was also kind of cool, yeah, so I think you're on, so live in different, I was kind of thinking a long time, or along the lines of the tide, so live in, because what was kind of cool about the reproductive patterns? So yeah, pretty fast too, but then what is helping them be successful, I guess? Yeah, the tides, so then, yeah, were you gonna add on to that?
Yeah, I was gonna say that, the tides.
So what about, so when do they lay their eggs then?
Probably at the high tide.
Or right after the high tide, right?
Say high tide probably gets them there. And then
Yeah.
low tide is when they do it, and then they probably get picked up at the next cycle. So
Yeah, or the
it's
eggs, yeah, I guess the eggs get picked out in the next cycle, exactly. So that's, right, it's kind of fascinating. So you have to think about it as these fish take advantage of this natural cycle. So after the high tide, then they deposit their eggs. And so, right, and then like you mentioned, so they come out of the water, they're in the sandy, or the watery, sandy beach there.
And it's the spring high tide too, so it's like the highest of the high tide.
Yeah, which is also kind of fascinating, right? So like, yeah, we'll emphasize that. So it's like the highest, right? So they take advantage. So they wait for like the worst conditions. Whew, then it's over. Deposit their eggs, and then after 10 days or so, then they're swept out to sea, and of course that helps them.
Wait, the eggs hang out there for 10 days?
They get buried under the sand.
Yeah, because they have to fertilize them.
How do
And,
they know in 10 days, oh, it's time to get washed away? They can't-
well, it's just,
Like when the next spring tide starts to come in maybe or something.
well, it's just, right, yeah, it's just the water takes them away, but they take advantage of the low tides, right, to do
So
the
tide
reproduction.
lessens after they're deposited, and then when it comes back, it takes them.
Yeah, it takes like the eggs out so then they can go live in the ocean. Yeah, because remember, it mentions too, because they have like weird kind of a weird fertilization. Yeah, because, see, look at, yeah, it's in the picture. Because they're doing the fertilization in the sand, it sounds like. Because, right, they have to have a way for, right, the eggs and the sperm to meet. But then fish don't have any sort of, like, you know, penis-like structure. This is why I don't teach biology. So then again, they take advantage of the low tide, and then they can do, right, their mating, so the eggs and the sperm have plenty of time, too, to, like, fertilize before they get all washed out. So it's kind of interesting, right? So it mentions, right, the guys curling around the girl, fertilizing the eggs, and so it probably keeps them there, you know, fertilizing, incubating. Because that's always the thing about, like, fish reproduction is they have to have a nice place to lay their eggs, and then for the guys to lay their sperm, and right, for them to stay together. So that's the hard part for fish. Yeah, exactly. Because it all, you know, all has to be timed perfectly too, the correct water conditions. So.
And then they die.
So yeah, that was
Like
kind of.
zombies when they get to the top. I don't know if you've ever seen one like at the end of their spawning cycle, but their like flesh is falling off.
Yeah, it's
Dark,
sad,
yeah.
man.
They look like zombies.
Yeah, that really big like chomper.
Oh yeah, that's from like their bodies changing from the salt water to the
Oh.
fresh waters. Their jaws get all. It's supposed to be able to attract mates, but like massive underbite with teeth sticking out.
Whatever the ladies find attractive. Anyways. And so last little bit is just like harnessing tides. So tides can kind of get trapped, especially if you have bays or different estuaries. And then you could, of course, connect that to some sort of turbine. So I think we mentioned this in the last chapter, right, getting energy from the tides. So again, same thing. They mentioned it. Again, these tidal power plants. All right, so I think that's good for 9. Feel okay about chapter 9?
Depends on the test.
I'll try to,
You have to take that one last time.
which, like I said, I'll try to keep it big picture. Oops. See, this is ridiculous. All right, chapter 10. So I kind of felt like chapter 10 was a little bit of like a summary recap. I know.
Keep it fun.
I'm trying. Recap of like our sediments chapter and kind of putting, it feels like a putting everything together chapter. I don't know if y'all got that sense. And so this is all about beaches, shoreline, and our coastal ocean. And, you know, I think we've been touching on this, especially with the sediment lab. So obviously we know different coastal regions have different features, you know, depending whether it's volcanically driven or whether there's a lot of biological activities. So they mentioned like Florida has a lot of seashells there. You know, obviously in Oregon we might see some little trees eventually, or, you know, tree particles making their way to the beaches. And so the beach is, of course, a dominant coastal feature, and many of us flock to the beach for recreational purposes. And we've been looking at the waves, and so again, we've already kind of been touching and dancing around how they can affect deposition and erosion. So of course, also thinking, right, runoff from the waters in the streams, so going into the oceans, but we're also mentioning going back to, right, our bay feature versus our jutting out. And we can right, go back to chapter 8. So they're all kind of building up. So all this that we talked about in 8, right, comes back up in 10, basically. So we mentioned all these features, how waves refract, how we have less energy, right, and that drives those sediment deposits versus where we have more energy, that drives erosion. So all of this, right, is kind of coming together in chapter 10. And of course, sea level changes affect the coast. And I'm sure y'all can tell me different stories, right, from different beaches, or I think we looked in past labs on the coast of Florida even, how one has a gentle slope, one has a drop off. So of course, all of that plays into everything. And we'll touch on, of course, how humans have attempted to live on the coast. Obviously, everybody wants to live on the coast. Good source of trade historically as well, and food, obviously. That's how you win settlers of Catan, right? With that. If you want to burn everybody, you got to get a port.
Is it like it everywhere, but I know at like Brookings and stuff, it's more mild climate than it is over here. Is that how it normally works?
Yeah.
Beaches is more mild.
Yeah, and that goes back right to our specific heat chapter and water, how all that. So yeah, we have, that's also why people like the coast, right? So a lot milder climates, doesn't get too hot, too cold. So yeah, all of that, putting it together. Good. All right, so we may have some labeling, at least potential fair game, right? So I haven't written the exam, admittedly. So that's my project. But this could be fair game. And so let's look at these different pieces. So first, we have the shore. And let's just look down. So right, our shore is just defined from our nice sandy beach to where our low tide is. So this is typically right where you hang out on the beach. So either you're hanging out on the dry sand, oops, playing volleyball or something, or maybe you're running on the beach. There's a guy running. So that's where, you know, the activities are occurring. And so our coast extends inland as far as ocean-related features are found. And so with that, right, we see our coastline, and our coastal bluff is included in the coast. So sometimes, right, you have a cliff from erosion, and then your sandy beach. So that's common feature of beaches. And so again, coastline, boundary between your shore and your coast. So right, your coast is just the little end after your sandy beach. And so now let's look at backshore and foreshore. So backshore is part of the shore above the high tide shoreline. So now let's look at that. Yes, exactly. So the dry sand area. So again, where the partying is happening. So party area. So the nice sandy part. Versus, so our foreshore. So notice, right, this is going to be exposed at low tide and submerged at high tide. So that's, and so again, that's why I said that's where people like to run. So it's where you have that area of like the wet looking sand. So of course it gets covered in the high tide. And then at the low tide, all that wet sand is exposed. And people like to run on it, right, because you don't sink like you do in the dry sand. And you make happy footprints in there too. Yeah, best sand castles in this zone. Of course, right, you have to time them appropriately, so you don't want to build them right as your high tide's going out. Have maximum time. All right, good, get beach experts. So then we have our shoreline. So let's look at where our shoreline is. So we have, right, our two different shorelines. So we can say we have our low tide shoreline, so obviously where the low tide is, and then our high tide shoreline. Again, our foreshore is between that. And so near shore, where's our near shore? So now it goes off the coast. So now it's from our low tide to our breakers out here. So now towards our, yeah. So breakers, so yeah, surfing would be out here. Try to draw somebody. Those guys having fun out there. Yeah. Might have to do like board surfing. And so now offshore is just beyond the low tide breakers. All right, so then we have our low tide breakers, so the furthest out, and of course, so offshore is now just anything past that. So beach, so we mentioned that, or our recreational beach. Let's see. Then our berm. So our berm is just out here. Again, usually where our beach is, just our gently sloping area right after the coastline. And longshore bars, so these are just sandbars parallel to the coast. So right, your longshore bars for breaking, so that just depends on either natural or man-made features. So sometimes, right, we attempt to put out some sort of breakers too. And then a longshore trough is what separates your longshore bar from your beach face. So right, some space there. Yeah, so dropping down. And then don't forget, again, your coastal bluff, your cliffs over here. You're welcome. And so like we've mentioned, right, all the different beaches have obviously different material based upon what material's around that makes sense. So of course, you know, whatever has eroded off your coastline would dominate. So again, depending if you had a big area, we mentioned of calcium carbonate cliffs, obviously that could lead to, right, all your calcium carbonate erosion. We've looked at volcanoes, looked at different areas. And of course, right, it also depends how it was deposited. So we mentioned, right, the energy that kind of dictates where things tend to crop up. So obviously boulders only make it so far, but then we have our larger pebble deposits. again, depending where they're coming from, but they tend to be around the beach versus a fine silt that ends up in the deep ocean. And again, it just depends where. You have to study each individual area, what's influencing it, what rivers are flowing in, what currents are bringing in sediments and dredging of sediments. And obviously sand and mud from rivers. We've looked at some biologic material, and this tends to be around, right, our tropical beaches where there happens to be more organisms. Right, so anytime we have a lot of life, we expect to find biologic material. And of course, material is always in transit. We see that, right? The waves going in and out, the tides. We mentioned too, they can have uneven reflected patterns, so that can sweep it along the beach as well. And so we have these two different kind of forces as they kind of define them. So swash is just when water rushes up the beach, and then backwash drains back to the ocean. And so kind of the balance of the swash versus the backwash determines whether stuff is being deposited and left on our beach or whether we're getting erosion. And then running parallel to our shoreline are going to be our long shore currents, and those just also move sand down along the beach. And so they have these two terms as well. So our summertime beach, that tends to be defined by lighter wave activity and generally milder. So usually there tends to be more deposition in these conditions, so more deposition of materials. So you can see our sand, right, coming up onto the beach at our summertime beach. And then with our winter time beach, we have heavier wave activities, so this means our backwash is going to dominate. And so that means sediment is moving away, so this tends to be a period of more erosion, again, relatively speaking. And this would lead to overall, right, your beach gets narrowed versus, right, your beach could get bigger in the summertime. And you could also get a flattened beach face, as again, you get erosion and stormy weather. And so these longshore bars again are going to be moving your sand. And so it's just comparing the two. So with our light wave activity, we're building up our sandy part basically, versus our heavy wave where the longshore bars tend to be built right out in the ocean versus the shoreline. That gives us different features. And again, this is associated with low waves. And again, right, light force. So once you have lighter energy, that's where you're going to get more deposition. So again, now we get our sandy beaches, ideally, right, a nice wide berm, versus heavy wave, where this tends to lead to a more rocky beach. And so this is our longshore current, so zigzag motion of water along a shore. And so you can see the currents are kind of moving to the right because, again, nothing approaches at a perfect straight-on angle. So everything's reflecting and pushing. And so this just pushes sediment down the coast. So it has different terms, so longshore transport, beach drift, or littoral drift. And so it transports our beach sediment in a zigzag fashion So, right, you have your current going in and out, and then it's moving it. Oops. So giving us our zigzag pattern. And again, you can see how this is moving across. Oh, and this is a good, I like this picture here, right? So you're imagining the wave going in and out, but it's also moving kind of down. So that's kind of associated with downward transport of sand and other sediments and material debris. And of course, right, millions of tons of sediment are moved every year. It's unimaginable what the ocean does. And of course, the direction of transport changes due to waves approaching. And so this is just kind of showing net sediment movement. And a lot of this, of course, somewhat follows the coast and looks like different longshore currents. So it moves the opposite of the Gulf Stream. So that's kind of interesting with this. I'm not entirely sure why that is. So there's two types of shores, and it's pretty nice, right? It's simple enough. So either you have an erosional shore. Oops. Oh, come on. Why did we jump? So erosional shore versus a depositional shore. And so an erosional shore, and we'll look at it in detail, but usually you have more well-defined cliffs. Could be where you have tectonic uplifts of the coast. And of course, our Pacific coast is one example, so it's pretty rocky here as well. Versus a depositional shore, where you might be gradually building some shore, and you can get some barrier islands forming naturally and sand deposits. All right, so let's look at our erosional shore. So as we might imagine, this is going to also occur around our headlands. So we mentioned that back in chapter 8. So those were, again, our jutting out areas. So look at anywhere the land juts out, it's going to be hit with more wave energy. And so this leads to pretty cool features. Have you ever been to Matador Beach, I think it is, in California? That's the one where it has like all these things like naturally. It's pretty, or maybe it's Malibu. I'm like, let me look, Matador Beach. Or maybe it is in Malibu, and that's why I'm confused. And it's just pretty famous because it's got all these nice little erosion features. So it looks pretty. And so, right, we get, again, our cliffs, our sea caves. So all these different things are cut out by wave activity. If things get stuck and start eroding, then, of course, eventually they'll break through. And so sea arches are just formed where sea caves and headlands erode all the way through, of course, if water, just depending where water is exerting the most force, plunge its way through. And then we have a sea stack from when we have no more sea arches. So there's this a little stack by itself. And of course, wind is another factor, so you can't forget about the wind eroding as well. But obviously, right, dominant force, the water, but I'm just saying other features, wind, erosion. So let's look at the picture so we can tell. So we have an uplift of wave-cut beaches. This generates a marine terrace here. And so wave erosion increases, of course, with more shore exposure to open ocean and a smaller tidal range, weaker bedrock, so all of that, again, you know, it depends exactly on the angles and everything, the currents, all that plays into effect. So now let's look at some examples. So this is off of Martha's Vineyard in Massachusetts. And so we have a depositional shoreline. Anybody ever been to Martha's Vineyard or anything?
A little too fancy for my liking.
That's what I figured. So.
What, you're not fancy?
Huh? It's like, who goes there?
You said that one.
I know. Oh, man. And, well, you know, we can see why this is a nice area. We have this depositional shoreline. And what's nice is they also have this kind of bay barrier. So it kind of seals off this little lagoon from the ocean. So that's also going to make this water probably nicer. And so a tombolo is just a sandbar that connects an island to the mainland. So here's a little sandbar deposition. And so this is apparently a Goat Rock Beach, which I'm not familiar where Goat Rock Beach is. It's like, hopefully you can't knock me for Goat Rock Beach. And so we can also, again, have those barrier islands, which are those long offshore sand deposits that parallel the coast. That can, again, offer some braking from hurricanes and currents. So there's our different features. So I feel like we may have mentioned delta in the past. I'm actually not sure if we defined that. So delta, right, where our river's coming out and meeting the ocean, so we can have deposits there. There's our split, where this can kind of water sneak in. So bay barrier, so it could be right completely enclosed potentially, or water can go in and out. And obviously that also depends on the tides and how they go around it. So either whether they go around or can completely cover the bay barrier.
Why is that one an island and not a peninsula? Because it's not surrounded by water.
It depends on the tide.
Yeah, because they has the tombolo, right, connecting it. So I think what they're trying to show is, right, you have this other mass out there, and then, like, sand was laid down later, right? So, like, this sort of thing. So they're calling this the island, and this, the tombolo, is the depositional deposits made later. So that's, I guess, their distinction, that the island wasn't necessarily, like, connected there. But
Can these things be, like, what if something was like man-made?
yeah, because you can have, like, man-made barriers and,
Okay, because so like, she'll probably know, but in Santa Cruz we have the cement boat. And it's slowly, like, well, I guess it's probably, I haven't been down there in 10 years, but when I was there, you couldn't even get on it anymore because it was falling apart. But the last time I saw pictures, it was like its own little island now, because it's just been
Yeah.
slowly being eroded away.
yeah, and, well, I mean, I think this chapter touches on that, but yeah, like, man-made features can turn into islands and other stuff, and, right, people try to sometimes build artificial barriers, so we kind of mentioned that with the hurricanes, is if you don't have a natural land, you know, sand deposited barrier or some other feature that gives you barriers, what can you put, what kind of breakers can you put, so that's all kind of related. What did you say it was called again?
The cement boat. It's in Santa Cruz. I guess it's actually probably closer to Capitola, but. When I was a kid, it was a restaurant. You could go in there and eat, and then it slowly started kind of floating away and breaking.
Crescent City has something like that, or Brookings, the boat, the museum.
There it is.
Yes.
That's not what it looks like anymore.
What does it look like now, even?
I'm pretty sure, I mean, you can't even get to it from the pier,
Wow.
Didn't like the pier break down recently, or like the boat sink or something like that?
Well, I know it's been slowly deteriorating over, because it actually used to be like a fully functional ship.
That's
And
cool.
it turns out, cement and concrete don't make good boats.
It's like Sucho Baths in San Francisco, used to be able to see the old swimming pools, but the waves have eroded that away now too, so you can't even see the old.
Yeah.
Sea cliff, that's right, that's what it's.
Yeah. And I think Belvedere Island in Marin County, it's like, that doesn't technically look like an island, but I think it's all man-made to protect it.
Oh, that's cool. Yeah, and so we'll touch on, because basically what we're kind of getting at is also kind of trying to find what I'm talking about. Oh, no, okay, let's go back. Because with these boats, or maybe I'm not finding the picture I'm thinking of. So right back to chapter 8, trying to find the right picture. Where was our little picture of our jetty going out? Oh, here we go, sorry. I was trying to find, because right, basically what y'all are getting at too, so anytime we have anything out there, so I'm thinking, in my mind, just looking at the picture of this, of our cement ship, right, it's almost gonna be acting like maybe a jetty, so it depends how solid that structure is too, so of course if it's like eroding. But yeah, it can either maybe reflect something or influence something, and
Well, I imagine that's what it's doing, because it's, now, I just,
Yeah.
picture, now it's pretty much that, just like a little chunk left.
So-
So it's been taking a beating forever, so it's probably acting as like a jetty.
yeah, and the next question that I was trying to ask Google, but I'm not finding it immediately. And I'm not finding the picture that I'm thinking of from the book right now in the lecture notes, but if I find it, I'll point it out. But you want to compare then, is what does the depositional deposit looks like over time? So you'd want to look, what was the land before they stuck that cement ship in there, and look at, right, the erosion or depositional patterns of that particular beach, right? And then see if you stick the giant ship there, does it change the erosion pattern? So that's, obviously we have to ask somebody, maybe somebody's doing that research, have to poke around and ask Google some more than rather in-class internet searches. And there was something in the book, I was trying to find it in the notes, but it mentioned, I think off the coast of Santa Monica, that there was like an artificial feature that caused different depositional patterns. No, I'm not finding. Not finding what I was looking at, because there was something where it showed the picture of they put this barrier out in the sea and then literally they got more beach, but I'm just not finding it. It was in California and I was curious, but I didn't look at it. All right, that's a little
I think it's
unknown.
on page 326.
Oh, yeah, perfect. That's exactly what I was talking about. Let's see if I can find it in these lecture notes. There we go. Is it here? Yes, finally found what we were trying to get at. Too many pictures. But yeah, so essentially, they put some sort of barrier out here. So they artificially deposited it. And so, yeah, that literally, right, it changed the whole shoreline. So that's why I was fascinated to know what did the ship do. So all of that influences. So right before the breakwater was constructed, you have your longshore drift, so it's like eroding your beach in Santa Monica. And then apparently they constructed a breakwater. And so, of course, that changes the pattern, right? Less erosion, so breaking up that longshore drift, and then they got bulging out. I just didn't look up if it's still here today.
Because after the breakwater was destroyed in 1983, the bulge disappeared.
Yeah, see? So there you go. Because, yeah, I was thinking, like, I'm not familiar with this bulge in Santa Monica in recent years, but it's just kind of fascinating. So, yeah, our man-made structures can change things. We can make or try to make barriers. All right, sorry for the jumping. And so, like we mentioned, we can have these nice little barrier islands. And so this can be over time from our long offshore deposits of sand. So, of course, traveling down a coast. So, of course, this would not exist among an erosional shoreline. So this is, again, depositional. And so, like we mentioned, this can protect the mainland from high wave activity. So now all these little islands start disrupting the waves. And so they said this area in particular seemed to have developed at the end of the last ice age, and I assume contributes to all the little features that you find. And so now, traveling down the Gulf Coast, and so again, we have these little barrier islands. And so, of course, people like building there because they're close to the ocean. But obviously, right, they can also get destroyed. Let's see. So all these tend to get hit during hurricanes. There's Corpus Christi, and South Padre Island off the shore of Texas. So all these. Oh, where's Galveston? Oh, there's Galveston. So Galveston Island. Right, so this one is comparatively right now a lot bigger. People live on Galveston Island. There's a lot of structures there, but of course they get the brunt.
Barrier islands man-made, or were they?
So these ones I think were also formed probably during the Ice Age. But yeah, these are all like naturally made, so these are not synthetic. And so here's just another example of a highly developed barrier island. So again, right, if they can obviously accommodate cities, just like an island. And so there's 2,000 barrier islands defined worldwide, and a lot of them exist along the Atlantic and Gulf coasts. So you can see all that, all these. So again, that's telling us depositional areas, especially over time and in the Ice Age. Depositional areas. And so eventually they are kind of migrating towards the land, but let's find a picture of what they kind of mean by that. So we have our barrier island, and right over time, so the ocean and wind and everything eventually kind of erode the material and bring it from one side to the other. And so that's why they say, you know, eventually it's migrating towards land, but again, very small over time changes. And so barrier island features, we have our ocean beach. So closest part of the island to the ocean. So that makes sense, right where we would imagine we'd find it, our ocean. And then our dune is the area behind the ocean, probably grassy. And this offers some protection, right? So all the roots of the grass helps hold all the sediment in place. And then our barrier flat is our grassy area behind it. And then we have our salt marshes, so just our inland area. And then our low marsh extends from our average sea level to the high tide. And then our high marsh extends to the highest spring tide line. So you can see right the different, our low line for a low tide, high line. Let's see, deltas. Oh, here's where we talk about deltas. So now we define deltas. So these tend to be triangular deposits. And so, right, they're flowing from the river. So high energy, so they tend to deposit triangularly, where rivers empty into the oceans. And distributaries are branching channels carrying sediment into the ocean. And so we kind of mentioned this before, at least with like the fans. So I don't remember which chapter that was where we talked about, right, the fans area spreading out, so all the deposits coming. Yeah, and we looked at the Mississippi River, so again, kind of similar things. Again, we'll get deposition. And when erosion exceeds deposition, then of course our shoreline is smooth and eroded away. And so apparently at the Nile River Delta, it's eroding, so this river is not bringing enough deposits to keep up, or it's meeting the Mediterranean Sea. So that's kind of interesting. And I think we've looked at that Nile current, right? That's kind of rapid. We'd have to look. I won't fumble for notes right now. All right, so we have our beach compartments. And so there's three major components. So we can have rivers, right, that supply beach sediment. So we've kind of talked about that. We have, of course, what's on our beach, and then any offshore submarine canyons and what that brings. So, right, our submarine canyon and all the sediments that there, what's there, what gets dredged up. And so looking at our different beach compartments, so it's just where we have everything bringing sediment. And then where's our submarine canyons that remove. So again, longshore direction. So all our little canyons. So areas of erosion.
So the canyons are all kind of at the tip of the little arrows.
Yeah, so it's like where our sand is leaving, and yeah, our tips, so high energy. So then we have emerging shorelines. So shorelines are above the current sea level, and we mentioned our marine terrace, which was just our flat area. And so we could have stranded beach deposits, so indication that our former shoreline has risen above sea level, versus a submerging shoreline. So shoreline would then be below your sea level, so drowned beach and submerged topography. And so now, kind of visual, emerging and submerging. So an emerging shoreline, So it's exposing more. So you might see, right, older deposits exposed, so ancient sea cliffs, and then our stranded deposits. So seeing all the layers over time versus submerging, and so where it's going and being eroded under. Okay, let's see. And so we kind of mentioned this before. So our two major things that can change our sea level are, of course, our tectonic movements. That obviously has an influence along with that isostatic adjustment. And this was back, I think, from our first few chapters where they say our kind of land mass is still rebounding from all the ice that they predicted was on it from the ice age. And you can go back to that little boat analogy for, right, our continents were in theory a little bit lower in the ice age, and now they're kind of still springing back up. And obviously all of that influences the sea level. Yeah, I'm going to post them after class today, especially since no one will update my laptop. So the eustatic level changes, so this is, again, just worldwide. Sea level changes, big picture things, right? Destructions of inland lakes or formations, so if water gets trapped too. Seafloor spreading, so everything, right? So this is huge impacts. Glaciers melting, freezing, all that. Even, right, minor. We looked at it, it was really small, right? Water contracting a little as it gets colder before it expands and freezes. And then also water, of course, would expand if it's hot. So, you know, I mean, you have to think about that on the huge globe scale, right? 70% water, and then that water even slightly expanding, contracting, all that leads to different sea levels. All right, so I kind of skip over that. So let's talk about kind of what we do to stabilize this erosion. So again, we've looked at this longshore erosion. And so we can do either some sort of outward projecting structure. We've kind of, again, hit on this. And I'm sorry I'm going fast. I'm trying to get through the chapter, and it's also a little bit repetitive, hopefully. So they call it a groin here, but just basically we have something jetting out. We saw that in chapter 8 too with our jetty, something that disrupts our currents. And perhaps you're trying to protect an entrance like we saw in chapter 8 with like the Newport Beach. And then of course this is going to potentially cause reflection of wave patterns. So all things to consider. All right, so we'll look at our four main stabilization structures. So groins, jetties, breakwaters, and seawalls. And so these groins are built perpendicular to the beach. And so it helps trap sand up coast, so trying to prevent that longshore current erosion. And so again, it kind of depends. So looking at this beach, it looks like they have several groins jutting out periodically to try to stop that erosion. And so jetty is similar. So the distinguishing feature is it's built specifically to protect your harbors, where your groin is just to stop erosion. So your jetties, like we saw in chapter 8, again, they would also be perpendicular. Of course, you have to have two of them to help, again, protect your harbor entrance. So there we go. And again, groin versus jetty. So jetty leads to our harbor. And so we've been kind of touching on the breakwaters. And so they can be constructed, so again, built now parallel to the shoreline, so designed to protect harbors from waves. And this, of course, can get eroded, so then you might have to keep adding to it. So, of course, that's a struggle, right? We're going to see with all these man-made barriers is obviously erosion still happens. And so there's that breakwater, or one breakwater at Santa Barbara. And like they park all their little boats there, so it's safer. And so we mentioned that breakwater at Santa Monica and how it again completely altered our wave. And so seawalls, I think we mentioned them with our hurricane chapter. And so they're usually man-made, so trying to kind of keep. So this is a nice diagram. So they're showing it on a barrier island. So I always think of Galveston, since Galveston has a seawall. And so Galveston's a barrier island. And so they have the seawall, so right, you literally build a wall to try to help. And of course, right, your seawall can of course fall into the sea potentially, always an issue. So like we mentioned with the hurricane chapter, it's also meant to provide, right, a break for the waves, so hopefully save the structures. But obviously, right, a whole storm can wipe out a beach, wipe out your seawall. And even so, right, there's generally a lot of erosion to seawalls. So they're under, obviously, they're going to be getting sprayed on a normal basis, salt, seawater. And salt is incredibly corrosive. You can even see that reflected in this picture, all that rust. So all those ions just lead to an increased rate of oxidation. And so, of course, some alternatives would be to restrict construction, but I don't know whether this actually happens or not. I feel like we just say that in theory and people still continue to buy beachfront property, but we won't go down there. And so if erosion gets really bad at a certain beach area, then they may attempt to do beach replenishment, where you truck in sand from somewhere to try to put it on. And there's also a lot of, not even going to get into all of it, but what's sand used for? Glass, yeah. So glass I liked a lot, but the big one I was looking for was glass. But then what's the issue with sand too and glass? What did you say? That's kind of what I'm going for. So basically, right, there's only like the certain amount of sand is considered like good enough for glass, and that can also lead to issues where they're like taking the good sand from one place and eroding the beach maybe even faster than obviously natural waves. And of course, with this beach replenishment, obviously it's very expensive to truck in sand from anywhere else. And again, where is it going to come from? Yeah.
There's a Hawaii in June, Waikiki, and the sand there is man-made. They've been trucking it in, so it must be an erosive beach, but they make it look like it's
Yeah.
depositional. But I thought that was interesting. The beach is kind of washing away, so they have to bring in this new sand so that they can keep this tourist area alive.
There's a mine in like the East Bay area, like San Francisco area, called Black Diamond Mines. They used to mine like sand for and stuff like that for like bottles, and then they stopped mining there because they found a beach that was better for it, or something like that.
Oh my gosh, that's funny. Yeah. According to a quick Google search, I was looking at Waikiki Beach, and they were saying that sand was trucked in from like Manhattan Beach in California.
I thought one of the locals said that it wasn't, that it was man-made. But maybe
Well,
it was
probably man-made beach, because you, yeah, because they, yeah, don't really manufacture like sand, but yeah, imported from somewhere, yeah.
That's so silly.
I don't know.
It's just silly though.
I mean,
Don't have enough
I
beaches, just
agree.
make one.
Which you were just saying, right? I mean, mining for sand is obviously very lucrative, like the correct sand, and I don't know what makes the sand correct or not, but yeah, so whatever they find a good area, it's crazy.
I think that mine, the sand was like a byproduct, because it was a coal mine originally.
Oh, that's cool. And so, of course, again, relocation, but no one ever wants to relocate. So let's see, trying to just get the last big ideas. So this is a lot about coastal waters. So let's skip this. We've kind of done this, and I'm not going to retest necessarily. Let's see. So this is just talking about, mixing, and obviously mixing of currents, all that. We've kind of touched on this before, but all the different densities. So, right, all we want to take away from this big picture, different densities causes mixing, right, adds to currents. And then obviously Coriolis effect, can't forget about that. So we're trying to finish up. So our estuaries, so all these little areas that we were looking at that were probably made by the Ice Age. So our coastal plain estuaries, these little islands here, so our barrier islands. So these are often associated with our tectonic plates. So right, one estuary is created by our downdropping of our faults here. And so again, big picture, either ice age or tectonic plates make these estuaries. So again, just little shallow deposits all over the place. And these are mainly defined, by their location. So you study the Atlantic versus our fjords over here. So that's what also their name is based on. So let's see. And so, of course, obviously human activities and estuaries go together. And these can be areas for marine animals. So, of course, any place where you have lots of shallow land and water, that can be good breeding grounds, like we saw with the fish, and good shallow areas or stiller waters or better nurseries. And of course, right, humans always have to balance their impact. So I'm just trying to finish the chapter. Does anyone know any much about the history of this? It mentioned the Columbia River, that this was pretty famous for getting damaged by the logging industry, but didn't know if anyone had a local perspective. Oh, like I'm not familiar with this, so I don't know. Like, is what the textbook says matches what you think is your reality?
Where's the I haven't gotten that far.
Oh, it talks about how the logging industry, like, messed up this, yeah.
So I know, for instance, like the Rogue, when everything was dammed, like we changed like the shape of the river. Like we were confusing fish. We were making it where it was harder for them to get through. So we were kind of playing God essentially by saying this is how the river goes now. This is how, and they were changing it on a regular basis.
Oh, man.
So I don't know if it was the logging industry, but there's a lot of issues and like polarized ideas about dams and manipulating the river and even hatcheries now. So
And it messes up the floodplain at the end of the river too, is kind of what it's saying here.
Yeah, because it was mentioning that there was like too many sediments and that messed things up, but
so
dams are.
And a big part of it is when you're throwing logs and stuff, or a big thing in like Klamath Falls was cattle was stomping the shorelines of the river.
Oh, yeah, I
and
remember.
pushing
Yeah.
And widening the river and making it shallower so it's hotter and dirtier and grosser, and so the fish population was like the ecosystems were just dying because of it.
Mm. So yeah, I mean, we could like go into, of course, a huge rabbit hole, especially, local issues. Again, that's why you got to get involved locally. So let's see, just looking at this Chesapeake Bay. And again, so big picture is just a lot of these are influenced by the seasons, the tides, right? We can have different, so changes in salinity, changes in temperature. So all that obviously creates, right, a complex ecosystem. So trying to, and so, right, it even mentions like the Chesapeake Bay, these waters, they don't have a lot of oxygen concentration, and so that can kill some of the, right, all the wildlife in that area. So that can cause issues. And you kind of touched on that, right? The agricultural runoff can create different blooms, and that's not good, and kill the fish. And so so lagoons, we just mentioned these were protected areas. So again, big picture. And this isn't that crazy. Again, we've kind of touched on this, right? Anytime you have mixing of freshwater, saltwater, you're going to have some more freshwater area, you're going to have some transition, and then some saltwater. And again, all that just relates to different densities. So just trying to keep this big picture so we don't feel like that we rushed through and didn't know. Is this right? We've kind of talked about this before. That's what helps drive little currents, little motion, all the different mixing, different salinity. So lots of factors. And so apparently this area is hypersaline. So again, just very regional focus. That's the other thing, right? You have to study each little area. What's the salinity? What's going on? What are the currents? What are the waves? So it's a lot of factors. All right, yeah, Mediterranean, nice, wonderful. Yeah. Mediterranean looks hot. Blah, blah, blah. That's probably. So again, big picture, coastal wetlands again, big east ecosystem. So yay. Right, you can have land animals, water animals going back and forth. And could be freshwater or coastal, so some mix. And swamps, so I think we already mentioned some of those cool, like brackish water condition animals. And so we can have, right, salt marshes with salt, mangroves, so this is just, right, obviously a lot of production is going to be around the rivers. We can even see that on our rogue rivers, right, where all the berries follow the river. So that's similar thing, just different areas. So mangroves instead of berries. And this is just comparing a salt marsh versus more of a mangrove, freshwater-ish swamp. But again, if you were asked anything, you'd be given a map to interpret. And obviously very diverse. Yay.
So it looks like the mangroves mainly grow between the tropics with Cancer and Capricorn, right?
Yeah, so that'd be a good observation. And so again, we mentioned farmlands could be an issue. And this is where things get complicated, but we won't get into because we're already over and out of time. But even so, you have to consider like the pH of the water too, so that can dictate how much nutrients are actually liberated in the soil and what gets run off. Blah, blah, blah. So yay, protect our wetlands. Happiness. All right, we'll end there. So take your 10-minute break. So we'll just make it to the 11:40, I guess. And yes, dogfish dissection today. But yeah,